Okay, so good afternoon, everyone. All right. Okay, so let's get started. As you can see today, I'll be doing the seminar by sitting here. As usually, I come with a box, so that's my podium. But today, I don't have the box. Why? Because my office has moved to S3. Okay, and uh, no, I cannot carry the box for such a long way. So this is how I'm gonna do it. Okay. All right. Let me see. One, two, three, four. We've got four people here. Well, I guess we all understand why. Indeed. So this is going to be the last seminar before the holidays. Okay, but not the last seminar of the whole series. We'll resume the series after the holiday. So that will be next year. Okay. All right. So today we're going to talk about actually something that's way more interesting than the first two talks on sampling. Okay. So the first two talks are basically paving the foundation, and things will start to get, let's say, more sophisticated. Okay. So today we'll look at one major technique, and this is called the Alias method. Um, So we will take our time to talk about this method inside down. All right. So first of all, let's define the problem that can be solved by this method. So this is very standard weighted sampling um, problem. All right. Now let's look at the definition again. Um, we uh, we talked about this. We talked about this. Yeah, welcome, welcome, please. We talked about this in the previous lecture, but today let's redefine it. Okay, so here we have a set of elements that we want to sample from. Okay, so once again, these elements, what these elements are, it's not really important. Okay, so this is the set S. And as usual, I'm going to use n to represent the size of S. Okay. Every element E, okay, in this set is associated with a weight. Okay, so this WE, this is something positive. All right, so that's the weight of this element. Okay, WE. Okay. And we want to do weighted samplings. What that means is we want to sample each element with a probability that is proportional to its weight. All right. But we have to make it a PDF, and therefore it's not surprising to see the following definition coming up. So this big W is the summation of the weights of all the elements in the set. Okay. All right. So in other words, our goal here, the goal of weighted sampling is to draw a random element from this set S such that the probability for this X to be a particular element in the set S is defined as the weight of the element divided by this big W. Okay, so this will have to hold um, for all the elements in the set S. Okay, so this is the weighted sampling problem. Okay. Well, just so you can study this problem from multiple angles. For example, one angle concerns whether you can do insertions and deletions in the set S. Okay, so today we're going to focus on the static scenario, static scenario, which means I give you the promise. I'm not going to change the set S. All right, so set S is just there. All right, I'm not going to insert anything or delete anything. All right, so this is known as the static scenario. Okay, so we're going to focus on the static scenario. All right, and then I'm going to comment on the dynamic scenario at the end of the talk. Okay, good. So because everything's static, and then you can see that this big W does not really matter, is what I'm saying, because you can always do scaling, right? So today, I will therefore set this W to be big W, sorry, to be 1, right? You can do the scaling, right? So that's why I said, we're talking about the static scenario, because this would not be something that's so convenient to do if you allow insertions and deletions, is what I mean, okay? So if you have a dynamic scenario like that, and then you want to use the full definition with this big W. Okay, so that will make it very rigorous, very formal. All right, so today we're going to assume that this big W is 1. So it's very interesting to note that the problem, in essence, essentially boils down to asking the following question. Suppose you have a discrete PDF. Okay, I emphasize this is discrete with a finite support. When I say support, I mean the input domain, of the PDF, right? So you can see that the support has a finite size, and also it's a discrete domain. Okay, the PDF itself is fully determined and fully defined by the weights of the elements, right? And then if you want to sample an element according to the requirement, basically this is just saying you want to sample from the PDF, from the distribution, right? So in essence, this is really a very fundamental problem because this is essentially saying, in general, if I give you a discrete PDF, how can you sample from it? Is what I'm saying, right? So we have talked about, for example, sampling with replacement. That's actually a very special case of what's happening here, right? So you can just assume that it's a degenerated PDF, a very specific PDF. But here we're talking about arbitrary PDFs. Okay. So as usual, I'm going to assume the presence of an oracle. Okay, so this is very standard. You have to talk about how you are allowed to generate random values, right? So we're going to assume that this oracle can generate a random value from 0 in constant time. Okay, I'm not going to talk about how to implement this, but in practice, um, this is usually specialized into specific situations because, in general, we won't be working with real values, right? So the reason why I mentioned real values is that, if you really want an oracle that can do exactly this, it's impossible according to our finite precision machines nowadays, right? But just so you know, in dealing with a concrete computer science problem, you don't really have real values. So typically what's happening is you will have rational numbers there. And then, yes, if it's a rational number, and then it will be able to implement such an oracle. Okay, but we're not going to be bothered with such kind of details because it's orthogonal to what we will be talking about. All right. Okay, so that is the stage. And we want to be able to do this with pre-processing. Okay, with pre-processing. Well, this is not surprising because if this PDF is a new PDF for you, right? Because if this is the first time you see it, and then you cannot hope to do any better than n time n. Because at the very least, you will have to go through the entire PDF, right? Otherwise, how do you know what is the distribution you are dealing with, right? So that would not be interesting. So instead, we'll be looking at this from a data structure point of view, right? So you want to pre-process this, and then you want to support the sampling operations, okay? So here, our goal today is to do this thing optimally. We want to be able to do linear space, big O of n, right? This is absolutely the best you can do because you need n space just to store the PDF itself. And also we want to do sampling time constant. Okay, constant. constant time, and then you can draw a sample, right? So basically, this is like as good as um, doing uniform sampling with replacement. Okay. All right. Cool. So before I talk about this alias method, which achieves these guarantees, I like to mention, I like to draw relevance to this tree sampling technique that we talked about last time. Okay. So that technique is actually much more general than just this particular problem. However, it does not achieve this constant complexity. Okay. Nevertheless, it will be interesting to talk about it because this is something very simple, and we just, you know, pick it up along the way, right? So how would you do this with tree sampling? Well, here is what you can do. You can create a binary tree. Okay, I said binary tree. I didn't say binary search tree. You see what I'm saying? Because the ordering does not really matter here. All right. So what you can do is you can create a binary tree on the set S. All right. You simply put the elements of the data elements at the leaves of the tree, right? So if you look at the height of the tree, you make it as small as possible. So that means log n. Um, and then this is the tree we're talking about in tree sampling, right? But recall that in tree sampling, we require that every node should carry a weight. You see what I'm saying? All right. So for the leaves, it's pretty easy, right? So for the leaf, let's say this is E1, and then the weight of this node is just the weight of the data element, right? Okay, so that's pretty trivial. And if you look at an internal node, let's call it U here, right? In tree sampling, we say that this node's weight will have to be at least, okay, at least the weights of its children, right? And here, binary, so there are two children here. Um, so how can you assign the weights to satisfy this requirement? Well, one easy way to do so is to define the weight of this node to be the sum of the weights of all the leaves that are underneath you. Okay, so basically you look at all the nodes here in the red subtree. Okay, so you sum them up and then you put the sum um, at u, right? So that will be the weight of u, right? And then you can see all the requirements are satisfied, right? Are satisfied, and then you can just go ahead and perform tree sampling here, right? So the space consumption is obviously n, and obviously you can build this in n time as well. What about the sample time? The sample time, we talked about it. We talked about the sample algorithm, right? So you just go from the root to the leaf, right? So sample time is just the height of the tree, which is log n here. Okay, so with this, and by the way, so I'm not going to go into the details. However, you will see that there's no failure here. There's no failure. Okay, intuitively, we don't really have this shadow interval. If you still remember, we talked about this is something we talked about last time. You don't really have the shadow interval at any node. Okay, because here the weight of a node is precisely the sum of the weights of its children. All right, exactly the sum. You don't really have sort of like strictly larger than the sum, in which case you will have some shadow interval. All right, but here you don't, right? So in return, what you get is 100% success. So you just perform um, one operation, and for sure that's going to give you a sample. Okay, so this is going to achieve log n time. But today we want to do better. Okay, we want to do constant time. Okay, all right. So towards first, we'll need to do much more work. Okay, it's not just tree sampling. Okay, um, so the alias method creates a data structure, which I'm going to refer to as the alias structure, okay, conveniently. Okay, so the alias structure. So I'm going to first define the alias structure. And then I'm going to talk about how to build it. I forgot to mention the construction time. The construction time of this alias method is also optimal. Okay, so you will see we'll be able to build it in just linear time. So everything sounds really cool here. Okay, I will first describe the alias structure, and then I'm going to talk about how to use the alias structure to perform sampling. And then in the end, I'm going to talk about how to build the data structure. Okay, all right. Okay, so I'm going to talk about the structure. All right. So I will focus on what I am going to need. Okay. So if this is the first time you see it, you might find it a little bit unusual, let's say, because this probably would not be how you do your own research. Okay, but just stay with me. I'm gonna be slow, but stay with me. Just focus on the mathematical meanings of what I'm gonna write down, and everything will be. I promise everything will be understandable. Okay. So the data structure essentially is a set of urns. Okay, so let's look at this word earn. Okay, so you see this word earn. That sounds very, let's say, ancient, right? It's a very standard word. I could have used buckets, but usually when you talk about balls and bins problems, people use the word earn. Okay, I'm just gonna play along here. Earn essentially that means a bucket, a container. All right. Anyway, so in this data structure is just a set of urns. Okay, but then as you can see, this is not a formal definition because you understand what a set is, but you don't understand what an urn is, right? So therefore, I have to continue, right? But overall, this is what I need, all right? A set of urns. And then I'm going to proceed to explain what an urn is, okay? All right, going on, for each urn, I'm going to talk about, what's happening there, right? So for each urn, okay, so let's say this urn, I use this lambda. This is the big lambda, okay? So I use this lambda to represent an urn. So for each urn, okay, there are only two possibilities. So each urn either contains just one element, E, all right, of S, obviously, or it contains two elements, E1, E2. All right. Now it's formal because now you know an urn is just a set of elements. Okay. And if I say, what is the size of the set? Well, simple, only two choices, either one or two. It cannot be zero. It cannot be more than two. Okay. Just one or two. All right. Good. I will need to store some additional information. Okay. So therefore, I will continue. Okay. So that's the first thing I want to talk about in earn. Now, the second thing I want to talk about in earn is for every element, for each element in this earn, well, now I have earned the right to write something like this, right? Because I have defined an earn to be a set of elements. Now I'm saying, just look at one element, okay? So here we want to store some value. Now pay attention. I said a value. I didn't say its weight. Okay, it's not its weight. This is actually the clever part, as you will see. All right. So we're gonna sort of like peel off some weight of this element and store the weight in this arm. Okay, that's what's happening, right? Just think about this as sort of like a pear, and then we peel it off, and then we store each portion in some earth. So that's what's happening. Okay, but formally, mathematically, no pear and no peeling. Okay, so mathematically, so here is our formalization. So we assign a value, okay? And this value we represent as v, so that's a function, but this function takes two parameters, okay? So this function v And as you can see, two parameters here, an urn and also an element inside the urn. Okay, good. So this value is greater than 0. Okay. Uh-huh. Yeah. All right. So that's the second thing I want to talk about in urn. But I'm not done yet. All right. There are more things doing. Okay, good. So now you can see two cases. This urn might either contain just one element or two elements. All right. So in either case, we require something to hold on the assigned values of those elements. Okay. So if only one element, if only one element in the urn. Okay, so I'm not gonna write everything down, but it should be clear, right? So this is the first case. And then it must hold that the value of this element is precisely 1 over n. Okay, 1 over n. Okay. So I define this data structure as a set of arms, which I represent as U, right? So let me just go ahead and tell you how many arms I'm going to have. Okay, I'm going to have precisely n arms, no more and no less. Okay, n arms. Okay. Well, why do I want to mention that now? Because I just mentioned 1 over n. Okay, so you can imagine sort of like each urn carries 1 over n of the probability in the whole probability space. All right, so this is very informal, but I think it will help, as you will see later. Okay. Anyway, so as I was saying, for each urn, there are two possibilities. This is the first possibility, and in that case, everything's very consistent, right? So the value we assign to the single element inside the urn is precisely 1 over n. Okay. But then we have another possibility, right? If two elements, E1 and E2. And then we also require something on their assigned values. Okay. And with everything I have said so far, and probably you will see this coming, right? So we require the sum of their assigned values inside the urn, okay, is precisely 1 over n, so that we can be consistent with what I just said, right? So this arm basically occupies 1 over n of the, the mass, is what I mean, the probability mass. Okay, so this is 1 over n. Good. All right. And yet I'm not done yet. Okay, I'm still talking about the urns. But this time I'm going to talk about urns from the perspective of elements. You see, so far I've been talking about urns from the perspective of urns, right? But then now I'm going to talk about elements. All right. So for each element in the data set S, now you can sense that this element has been chopped off into a lot of pieces. You see what I'm saying? Okay, so it's like one piece in one urn. Okay, and however, one element might have multiple pieces, which means this element might appear in different urns. Okay, and in different urns, they carry different values, is what I'm saying. Okay, good. So we place one requirement, and this requirement is very, very intuitive. It says, okay, if you look at all the arms containing this element, okay, now remember, in every such arm, you have assigned a value of this element in that arm, right? So this is really like how much you have peeled off, right? So if I sum them up, what do you get? What do you get? Come on, you know it, right? So this will have to be the probability of this element, right? So this WE, right? WE is just the probability in the PDF because we're saying big W is 1, right? Okay, cool. That's it. All right, so that's the data structure, right? Right? This is data structure. So Um, don't worry about how to create such a data structure. How come it's even possible to have such a data structure, right? So that's why I said if this is the first time you see it, you might find it a little weird because this doesn't look like a binary search tree. It doesn't look like, whatever anything you are familiar with. But just tell me, right? Is this a data structure, right? Okay, you cannot argue against that fact, right? All right, so you don't have to worry about how to create the data structure. Leave that to me, right? But just think about it. How much space do you need in order to store something like this, right? Okay, so you can see in every urn. Okay, wait a second. Let me just get this thing away from you. Um, High caption. Okay, so this is not helping. um, and I don't know how to get rid of this ribbon. Join video, join with video. Okay, so now it goes away. But we want to do this. Okay, turn up. Okay, I'm fighting with the software now. That's interesting. Okay, and still it doesn't do what. Oh, okay, now it goes away. Cool, cool. All right. So how much space do we need in order to store this, right? Think about it, right? How many arms do you have? You have n arms, okay? Now inside each arm, what do you need to store? Well, either one element or two elements. But in addition, you also need to store for each element a value, all right? But still, I mean, come on, just like four things to store in the worst case, right? So that's absolutely constant space, right? Okay, so you have n arms, and therefore the total amount of space consumption is big O of n, right? No problem, right? All right, so I have um, held up my first promise, right? The space consumption is n. But then the next question is, if you already have the data structure, how can you draw a sample? Okay, so this is the second thing. Still, I'm not talking about how to build a data structure, right? But just imagine that someone has given you this and say, okay, you know what? Use it for the purpose of drawing samples. Okay, so what can you do, right? Okay, and then we're going to talk about um, building the data structure. Okay, good. So now let's talk about the sampling operation here. Okay. So we want to do constant time. Don't forget that. Okay. So I want you to really have a strong intuition about this while listening to me, right? Because I have tried very hard to give you this analogy of how much probability mass is being carried by each arm. Okay, so you can imagine overall we have this probability 100%, right? And we have got n arms, right? So each arm occupies 1 over n. And you know what, the good news is that's equal for every single arm. Okay, there must be something nice about this, right? Because if we want to do constant, if you think about it, you want to do constant. I mean, not too many data structures will allow you constant time operations, right? We could be talking about hashing, right? But there's no hashing here. I can promise you that, right? There's no hashing, all right? So other than that, what else? Well, linked list, stack, and queue. No, they don't sound right in this scenario, right? So basically the only data structure that will give you constant time access is what? Array. Thank you very much. Very good job. So array. So now you can see everything should somehow eventually get connected to an array, right? So now if you connect all the dots, hopefully this will allow you to never forget what's going to happen. All right. So basically, you can imagine, an array here. So each array, sorry, each cell in the array is an arm. Okay. So this is arm number 1, and this is arm number n. Okay. So the first thing you want to do is you want to, randomly pick an arm from this array. All right, so that's a constant time doable. So that is exactly the first step. Okay, so randomly, actually this means uniformly at random. Okay, but I think this should be quite clear. Randomly, pick an arm. Okay, so let's say this arm is lambda. Okay, all right. So now you are convinced this is the constant time doable. Now, and then we look inside lambda, right? Okay, two possibilities, right? So lambda could be having just one single element or two elements, right? All right. So let's talk about them one by one. So if lambda has only one element, let's say E, all right? So what are you gonna do? You will return E. That's your sample. Nothing else to do, okay? Return E. All right, that's pretty cool, right? Well, that's the simple case. Well, let's say if it has two elements, E1 and E2. Okay, now you have to toss a coin because there's something to select, right? So either E1 or E2, right? But it should be fairly intuitive what you should do, right? Because every E1 and E2 has some peeled portions, right? Not the entire pairs. You know what I mean? So E1, that's an entire pair, but inside this uh, urn, there's a little portion of it, right? How much? Well, for E1, that's V, E1, sorry, V lambda E1, okay? So that's a tiny little value because this has to be less than or equal to 1 over n, actually strictly less than 1 over n, right? Okay, so for E2, you also have another tiny value, right? But these two values, they do not really add up to 1. You see what I'm saying? If you want to choose between them, um, with probabilities proportional to their weights here inside the arm, you really have to do the normalization. You see what I mean? Because why am I dividing everything by 1 over n? Because don't forget, right? We have this requirement that the sum of these two assigned values is precisely 1 over n, no less and no more, right? Everything's very precise here, 1 over n. So if I divide both values by 1 over n, and now you have a coin problem. It's just that it's not a biased. It is a biased coin. Okay, it's not a fair coin. So what I mean? All right. So how do you choose between these two values? Now you toss a coin with, let's say, heads probability. This the value on the left hand side, right? So if it comes up heads, and then you pick E1, otherwise you go for E2. That's it. Okay, that's it. Again, that's something you can do in constant time. No problem, right? Because we have this oracle to help us with. Okay, very nice. So that is only 50% of the journey for sampling algorithm, right? Because this is only the algorithm. So the most difficult part usually is not the algorithm itself, right? So the good stuff is in the analysis. So we have to understand how come this is achieving the purpose of, weighted sampling. Okay, so don't forget, you have to argue that this X, which is the element that you return using this procedure, right? So this X, by the way, is a random element, and that's for sure. Okay, so this X, no matter what you do, this X will have to come from this set S, right? No problem about that. But the thing is, you have to argue that the probability of this X, it's a random variable, so it has a PDF, right? So you want to argue that the PDF of this X is precisely the same as the original PDF. Okay, so everything will have to be precise again. All right, so we don't allow a single discrepancy here. Okay, so if that is the case, how do you prove two PDFs are completely the same? Well, one stupid method, okay, one stupid method is simply to compare the PDF values, at every single possible element in the input domain, right? So therefore, now here our goal. Okay, so this is a very stupid way to prove equivalence between two PDFs. Nevertheless, this is the way we will approach. We'll adapt. Okay, so the goal is to prove that the probability for X being any particular element. Okay, so this yi, what is this yi? This is an arbitrary element in S. Okay, simply to look at the support, right? So this is support, this input domain, right? So you want to analyze the probability for X to be yi. So there is a probability for that event, right? So you want to convince yourself that this is precisely WE. Okay, so that is the goal, right? If I manage to convince you that this is true, and then essentially I'm saying, look at this PDF of X and also the PDF of the weights, right? And they match exactly at every single point. And what else do you want? So that's sufficient for proving the correctness. Okay, good. All right, now let's prove it. Okay, how come this is true? Okay, well, let's prove it. So for this element E, we know that it appears in at least one urn, right? Potentially, it could appear in multiple urns, right? How many in the worst case? N. Okay, it's possible for one single element to appear in all urns, right? However, remember, their little pieces will always have to add up to the weight of this element, right? Anyhow, I can I have the right to say, let's look at all the urns containing this element. No problem with that, right? This is my right in the proof. So this is what I demand. You first show me, the set of urns containing containing what? Containing E. Okay, good. All right. So I don't know how many such urns there are. So I'm gonna just say, okay, you know what? Let's say there are T of them. Okay, so T is at least one. It can go up to N. And at this point, I can adopt the following notation. This is my right, right? When after I have got here, then I can say, you know what? I will represent those urns as lambda 1, lambda 2, all the way to lambda t, right? So you see, I don't demand anything I'm not entitled to, right? Okay, good. Very nice. So now I analyze this event, x equal to e. That's a random event, right? That's a random event. Good. So you see this random event, this random event can be decomposed into t events. Okay, why? How? Look, you say that this algorithm returns e, okay? But this algorithm always returns something from the urn that it chooses in the first step. You see what I mean? Look at the two-step procedure here, right? So the first step chooses an urn. You see what I'm saying? Okay, good. So if X is E, so this means that there are only T possibilities here, right? Depending on which of the T urns you have discovered this E. You see what I'm saying? All right. So I'm going to define T separate events. Okay, so I represent those events as E1, E2, all the way to ET. All right, precisely this EI is the event that the algorithm returns E from the urn lambda I, right? Fair enough, right? Okay. So now I know that the event X equal to E is cut into T, is decomposed, right, into T disjoint events, right? They are disjoint, all right? They don't overlap. And therefore, this is from the basic definition of probability. I know that the probability of this event is the sum of what? The sum of the probabilities of all the disjoint events there, right? So I being going from 1 to t, I look at the probability of each event here, right? So I sum them up, and then this equality should hold. All right, good. So what is nice about this is that now I can really focus on each EI. Okay, so I will analyze this probability of EI and everything symmetric, right? Good. So now let's think about this EI. All right, so this event. So this event occurs if and only if two good things happen. Okay, the first good thing that should happen is that if you look at the algorithm, there's a lambda, right? Chosen in the first step of the algorithm, that lambda will have to be lambda I, right? Because now I have EI, I have the I there, right? So now I can say this is the first thing that should happen. You see what I'm saying? And then the second thing that should happen is that, the second step picks E, right? So these two events, both of them happen if and only if EI happens. This is if and only if, right? Good. Well, you can see these two events, they are independent. I mean, these two bullet events, right? They are independent, right? And the probability of the first event is actually very, very clear. That's just 1/n, right? Because every herb is picked with the same probability, right? So the only thing left to analyze is what is the probability of the second bullet, right? Okay. Well, let's look at the second bullet, right? So there are two possibilities, right? There are two possibilities. So the first possibility is this lambda contains just E, right? And that should be 100%. You see what I mean? That should be 100%. And then I'm going to write this 100% as follows, right? So I'm going to write it as, so the probability should be 100%. Okay, let's write it down here, 100%. Okay, but it's not the 100% that I need later. Okay, I need something that appears to be in a different form, but it's really just 100%. So what is that? Okay, look at this very carefully. V lambda E. So this is the value of E assigned, inside this urn, right? And in this particular case, we know that lambda has just one element E, right? So by the construction, actually by the definition of our data structure, this is precisely 1/n, right? 1/n. So we say, this is this value divided by 1/n, and there you go, right? So this is 100% probability, right? Okay, so I will rewrite this a little bit. I will write it like n times v lambda E. This is a little bit more natural, right? Okay, good, right? So this is the first case, right? Now let's look at the second case, and you will see why I really like that expression, because the same expression is going to come out again. Okay, now let's see. Well, if you have two elements, right? So there's another guy, let's say E prime. I don't care about E prime, right? But E is selected from this lambda in the second step, right? But what is the probability of that? Well, our second step, tosses a coin, right? So this is a biased coin, right? So we know that, E will be selected if and only with the probability, like I said, right? So this is the assigned value, E, right? And the other guy, E prime, has also an assigned value, right? Now remember, these two assigned values, they sum up to how much? 1/n, right? So we know by this biased sampling, what we do is we end up sampling this element E with precisely this probability. Okay, so this is once again n times this V. Okay. It doesn't really matter, what case claim that the probability for the second bullet is precisely the value assigned, that's V lambda E, okay, divided by 1/n. All right, so that's basically n times this value. Okay, good. Very nice. And now you can do the simple math. All right. I'm going to do it here. So now you can calculate the probability of X being E. Okay, so the probability of X being E, as I said, this is the probability, the sum of the probabilities of all the EIs, events, big EIs. But you know, the probability of this big EI, we have analyzed it. This is the product, 1 over n. And another thing that depends on the value, the value assigned to this element in the corresponding urn, which is lambda I. Okay, so you simplify it and then you get the summation of the assigned values of this particular element in all the urns. Well, you know, I do have one requirement. Oh, I erased that, unfortunately. Okay, but remember I had a requirement there. I said from the element's perspective. You still remember that? I said, you know, all these assigned values will have to be precisely W. Okay. So that's a smart algorithm, huh? If you think about it, right? Because you know this weighted sampling really appears to be much more difficult than just sampling something from the array, right? But eventually, as you can see, this is precisely one of the key ideas used by this algorithm, right? So this is very smart if you think about it, right? It says, okay, you know what? You cannot really do this random access directly because it's not uniform sampling. But how about you create something uniform? Right? So this is so smart, right? It's so smart. You create something uniform, and then and then the next question is, okay, I gotta do that very carefully because if I'm careless, you know, even though I could make something uniform, but then inside every urn I could have lots of stuff, right? Okay, but what if you don't have lots of stuff, right? What if you have just a constant number of stuff, right? And indeed, if you have one or two, and then everything checks out. So now the only thing to convince you about is that you know there is a way to build this data structure, right? So how can you make sure that in each urn there are at most two elements that you need to? So based on the array here, even if we not construct a uniform array, we still construct a sorted array with a binary search. You don't need the tree. Actually, the tree itself is one convenient way to talk about everything. Yeah, we can construct a sorted array with the CDF of the elements, and then yeah, be sample to some segment. We can do a binary. Oh, absolutely, absolutely. So if you want just log in time, right? Yeah. There are many ways to do it. For example, you could use this idea that I talked about last time. You know, you consider this 0 to W as one interval, right? And then you can break it into a lot of segments, right? And you can break it into n segments, and the length of each segment is just this WE, right? So that would be another way to do it, right? Okay. You know, tree sampling is one way to do it, but login time, you know, there's more than one way to do it. Yeah, but I just wonder why if some method is intuitive and simple, you don't need to maintain a tree. You just okay. So maintaining a sorted array is actually harder than maintaining a tree. So if think about it, right? So if you have a binary search tree, right? So you can perform insertions and deletions there. But if you want to maintain a sorted array, that's pretty hard, right? But here you don't really need to maintain a sorted array though, because all you need to do is just to make sure you have everything inside this basically the segments, right? Inside this big segment. Okay. Well, anyhow, login time is not so interesting after we have heard, you know, what the alias structure can do, right? Okay. Nice. So I think at this moment, everybody should have a very firm grasp about this data structure, right? Okay, so I'm gonna open up a new page and then I'm gonna talk about how to build it. Okay, good. Very nice. Okay, so now you know we have n urns to build. Okay, And obviously, at least at first glance, I would say the obstacle is that these elements, they have arbitrary probabilities. Okay, so how can you reconcile this thing with this Orrin idea, right? So this algorithm, this building algorithm, performs n iterations. Okay, so let me talk about this algorithm in a top-down manner. Okay, I'm going to give you the big picture first, and then I'm going to refine on the details. Okay, and iterations. Okay, so I can tell you in each iteration, I promise I'm going to do the following. Okay, I'll do the following. So I will create a churn, not churn. I'm sorry, an earn. I will churn now and earn. Okay, so I create and earn. That's the first thing I'm going to do. Okay. So the second thing I'm going to do is I would definitely remove an element from the set S. Okay. Remove an element from the set S. Okay. Definitely remove it. Okay. After the first iteration, for example, you'll be having just n minus one elements left, etc., right? And at the end of the algorithm, you got nothing left. Okay. Now, also possibly, I would do one more thing. What's going on? Possibly, I will also adjust, okay, adjust the weight of one more element, of another element, let's say, another element. Okay. So I would definitely do the first two things, but possibly also do the third action, take the third action. Okay. So this is how an iteration is going to pan out. See what I mean? And I will have n iterations. Okay. All right. Now, in addition, I'm going to stick to an invariant. Now, this is something that you can check. Okay. I will stick to an invariant. So this invariant says the following. Invariant means something that I will stick to. Okay. Something that's not going to change. Okay. So this invariant says the following. Before iteration I, so this I goes from 1 to n, right? Okay, before iteration I, the following should happen. So first of all, if I ask you, how many elements there are in the set S now, at this moment, before iteration I, okay? You know, I minus 1 iterations have been performed, right? And according to what I said, every iteration removes one element, right? So precisely I minus 1 elements have been removed, right? So here, the size of S is precisely, n minus I minus 1. So this is just n minus I plus 1. Okay, so this is the first thing that should be happening, and this is easy to understand, right? But what is important about this invariant is actually the second thing, right? What's important here is that the sum of the weights of all the elements in S currently, okay, in the beginning, the sum is 1. You know it, but not anymore, okay, starting from the second iteration, all right? The sum of the weights of all those elements is precisely m minus I plus 1. That's the size of the set S over here. Okay, so that is the invariant. Okay, well, this is very easy to believe. Why? Because I have, at this point, I have created how many urns? I have created I minus 1 urns, right? So each urn should occupy how much probability mass? I told you 1 over n, right? Okay, good. So 1 minus a fraction, I minus 1 over n. What do you get? You get exactly this, right? So this is essentially saying what is the probability mass that remains to be assigned to the upcoming urns, right? So again, everything should be very intuitive and believable. Okay, good. Very nice. So as you can see, I have basically the entire thing mapped out for you, laid out in front of you, right? This is how the algorithm is going to work. Yeah, I'm pretty sure, many of you will be able to take things from here. Okay. Well, anyway, let me complete the whole story. So let's see the algorithm. Okay, let's see the algorithm. So the algorithm works as follows. The first thing, now let's talk about iteration I. All right, now I goes from 1 to n. All right. So you first check, is there an element, say e, with weight precisely 1 over n? All right, so that is the first question you like to ask. Okay. By the way, when I say weight, I mean the current weight. Okay, current, because the element weights are changing from iteration to iteration. Okay, so what I'm saying is currently, okay, is there an element in the remaining set S, and this element's current weight is precisely 1 over n. Okay, all right, so two possibilities, yes and no, right? So if so, okay, if yes, all good, all good. So this is the element you want, right? So it's right there for you. You don't have to assign anything. You see what I'm saying? It's there. So it's the designated element that you want to use to create a new urn with. You see what I mean? Okay. So create an urn with just this element E. Okay. So let's say the urn is lambda. Okay. Assign this value here V to be just 1 over n. Okay, remove E from S, and that's it. Okay, so once again, the idea is, this urn should contain 1 over n of the probability mass, right? And you have exactly one element whose current probability mass is 1 over n, right? So all good, right? So now you take this element and you place it there, right? But then you have to remove it. You see what I mean? You have to remove this element from F. So now you can see if the invariant has been upheld so far at the beginning of the iteration. And then after what we have done here, the iteration will be correct for the next iteration. You see what I mean? Because I have just removed 1 over n. And look at these 3 bullets here, right? So that's exactly something I have, not exactly, I mean, I have done only the first 2 bullets, right? But I told you the 3rd bullet is optional, right? Okay. All right, so if not, okay, well, if not, and then you cannot use just a single element. Now here, just another clever observation we can make here, right? So you can see we have this invariant. So this invariant tells us what? Tells us at this point, we have n minus I plus 1 elements left, and the sum of their weights is, n minus I plus 1 divided by n, right? So on average, think about these are the student scores, right? So what is the mean? What is the mean score? The mean score is precisely 1 over n. You see what I mean? Okay, good. So no one, on the other hand, has the score of 1 over n, right? So this means what? It means you can find somebody with score less than 1 over n and somebody with score extremely larger than 1 over n, right? It's not possible for everyone to be below 1 over n and everyone to be above 1 over n, right? So that's very nice, right? Okay, good. So if not, you find an arbitrary element, E1, with current weight, okay, so I emphasize this current weight less than 1 over n, okay, and another element with current weight greater than 1 over n. Okay, So these are the elements you want to use to create a new urn with, all right? But then you have to do it carefully because you want to satisfy the 3 bullets, and also you want to keep the invariant for the next iteration, right? So, but I think at this point, it should be fairly clear what you should do, right? So create an urn with these 2 elements, E1 and E2. Now you want to assign the values, for the element with the smaller score or weight. That's pretty easy, right? So just the weight, just the current weight of E1, right? And what about the other value here? You want to peel off certain uh, part of E2, right? So you want to set the value to be 1 over n minus what you have from E1, right? So that you can make an urn where the 2 values sum up to precisely 1 over n, right? But then, as I said, you have to make sure that this invariant should hold for the next, right, for the next iteration. So currently, if you do not do, by the way, if you do not do the missing step, the next step, this invariant is not going to hold. You see what I'm saying? Because the weight of E2 is still there, right? So, you have to adjust it, right? So reduce the weight of E2 by, what you have placed into this new arm. Okay. So this is the second case, right? Now you can see everything I have promised you has been honored, right? So that's exactly what I do in each iteration. And for the next iteration, you can see that the invariant still holds, right? So that's it. All right, that's it. Well, the only thing I've not talked about is how you can implement every iteration in constant time. Okay. Well, I will give you a very brief explanation. Actually, that's something I would like to leave as an exercise for you to think about, because this will be very interesting for you to think about. Okay, so that's exactly the algorithm, and how can you implement it in constant time? You cannot afford to maintain, for example, binary search tree, right? You search something, one search in the binary search tree, you're out of your budget, right? Yeah, exactly. Very good. Right. So all you have to do is use, let's say, 3 linked lists. Okay. One linked list containing all the elements whose current weights are precisely 1 over n. Now another list with all the elements whose current weights are over 1 over n. And then another list with the remaining elements, right? So now you can see one element. Well, anytime you want to select an element from a list, it's just constant time, right? So that's how you can implement, for example, this yes case in constant time, because if the first list is non-empty, just grab the first one, and that's it, right? Now, if you implement the second case, it's possible for an element to currently appear in the list for larger than 1 over n, but after its weight gets reduced, it might move to another list, right? But that's again something you can easily achieve in constant time, right? Okay, so now that's everything I have to say about the alias method. All right. Okay, so I guess I will see you next year. Okay. All right. Okay. Bye bye. Yes.